Okay, well, I'll have to upload 2 videos. Hopefully the other one went through. All right, so yeah, when you look at this problem, you see the diagram, you see the loop, you should be thinking vertical circular motion. But here, we don't need it. We don't need vertical circular motion concepts because, again, the only thing really, that we're just looking for the speed here. The only thing really that's happening is that we're changing elevation and we're changing speeds. The path that we take as we go from A to B doesn't matter, right? I could have gone straight down this way. I could have gone down, up, around, and then back to there. It doesn't matter. The path, when we're talking conservative forces, the path that you take between 2 points doesn't matter. The work done by those forces is the same, regardless of the path that you take. So, that being said, I don't actually need to use circular motion concepts here. Again, it would be far too difficult anyway. So I can just use conservation of mechanical energy. Now, I will still be saying in my head, I bet subsequent parts, I bet I'm going to have to do some circular motion stuff because this is a long FRQ. And yes, we're going to have to do that. But for this particular question, we're looking for a final speed. And all we're doing is changing elevation and changing speed. So I can just use conservation of energy again. So I'm going to say the initial mechanical energy is equal to the final mechanical energy. Now I'm going to say, I'm going to put a B there just to indicate that the final mechanical energy when the object is at point B. So expanding this all the way out, initial gravitational plus initial kinetic equals the gravitational at point B plus the kinetic at point B. I start with 0 kinetic energy because I started from rest. Note that I can't cross out either one of these two though. Because at point B, I have gravitational potential energy, right? It was all kinetic at point P, but as the object moved up, it started taking some of that kinetic and transferring back to gravitational potential. And so I have both types of energy here. So don't get in the habit of always crossing out one on either side. Chances are at least one of them will be crossed out depending on the problem, but you can't assume that. Okay. So my initial gravitational potential, again, it's just mg times that initial height, y naught. And then that's going to equal my final gravitational potential, which is mg times my final height, y, plus 1/2 times the mass times the velocity at b squared. And that velocity there is what I'm looking for. Everybody brought mass to the party. So gy naught equals gy plus 1/2 velocity at b squared. And I just subtract acceleration due to gravity times final position. And I get gy naught minus gy equals 1/2 bb squared. And because I'm a huge nerd, I see this, and I'm like, I don't like writing it like that. I'm going to factor the g out, and I'm even going to take another step to do it because I am that much of a nerd. It's a good habit, though. It's a good habit. It simplifies your expressions, right? That's part of simplifying expressions, is factoring and stuff like that. You don't have to do that, by the way. You don't have to. But I think it looks neater, so I like doing that. Multiply both sides by 2. 2 times the acceleration due to gravity times the difference between our final and initial position. Difference between our final and initial positions equals velocity of point B squared. And then I just square root both sides. And I get that the velocity at point B equals the square root 2g times the initial position minus the final position. And then I just plug and check. So my velocity at point B will be the square root of 2 times 9.8 times my initial position, which was 90 meters, minus my final position, which is 50 meters. And obviously we can all do this in our head too, and it comes out to 28 meters per second. And that should make sense. We're moving slower now. than we were at the bottom. We're moving at 42 meters per second here, moving at 28 meters per second there because we lost some of our kinetic energy at the expense of gravitational potential energy, so we had to slow down on the way up. Sound good? Now this next problem. On the figure on the car below, on the figure of the car below, draw and label vectors to represent the forces acting on the car when it's upside down at point B. Anytime you see something that says draw vectors that indicate forces, that's free body diagram, right? Free body diagram. So here's my car. It is upside down at that point. So I'm going to draw the track to the circular track. Pretend that's a circle. What forces are acting on that guy?
Friction.
Friction and
Normal.
wait. Friction and frictionless. This is a frictionless track.
Okay.
It says that.
Gravity.
Gravity. Someone else said the other one?
Force normal.
Normal force. Force normal. Yep. Nothing else. Nothing else. Yes, there's actual friction and actual air resistance, but we neglect those. All right, that's part D. Those are easy points there. Don't miss the points on the free body diagrams, guys. Yes, ma'am.
Do you have to include anything that like keeps the car to the track, or?
That's what there's no force required to keep it stuck to the track.
Okay.
Remember, it's moving in a vertical circle, so it wants to travel in a straight line. So really, what's keeping it from moving in a straight line, or really it would be a projectile, but what's preventing that is the normal force from the track pushing on it. If you didn't have enough speed, then you would require some kind of force to keep it stuck to it, but you don't. And that's like the big misconception here with circular motion, vertical circular motion. You feel like there should require some force to keep it stuck. And so that's what people call centrifugal forces, but those forces aren't real. It really, what the forces that are at play at this point are preventing the object from just moving out this way, right? Because at a pretty high speed this way, it's actually going to go outside of that circular arc of the track. It'll be a projectile, but it'll come out this way. So what prevents it from moving out there is actually the force of the track pushing on it, pushing it towards the center of the circle. That's a good question. That's a very good question. And that's something that you want to definitely understand if you really want to know the physics of it. Okay, now part E says calculate what those forces are. Well, mg is an easy one to calculate. Mg is going to be 700 times 9.8, which I don't remember. 6,860. 6,860 newtons. That's the easy one. The hard one is going to be the normal force. And this is where you really got to understand. This is stuff from previous unit. Now we got an object that's moving in a vertical circle. When I'm trying to calculate forces, I tend to use Newton's laws of motion. I didn't need to use Newton's laws for the weight force because the weight force is easy. If you know the mass, you can calculate the weight. You multiply the mass by g and you got the weight. But if you want to find any other force, most other forces, you got to use Newton's laws, Newton's second law. The object is definitely accelerating. It's moving in a circle. So I can use Newton's second law. It says that the net force is equal to the object's mass times its acceleration. For vertical circles at the very top and at the very bottom, we can use the uniform circular motion equation because the forces at the top and at the bottom are entirely centripetal. So we can call those centripetal forces and centripetal accelerations. The net center-seeking or centripetal force is the normal force plus mg. You just add them together. The ones that point towards the center of the circle are positive. And remember, we have this expression for the centripetal acceleration. Speed squared over radius r. So the right side is going to be m speed squared over r. And that is the speed at point B, which we've already calculated. Okay, calculated here. So now all we need to do is subtract mg from both sides. And we have an expression for the normal force. Normal force is mass times the speed at point B squared divided by the radius minus mg. And what I would do, just because I feel like it's a good habit, you could plug and chug. This is a valid answer. If you didn't have numerical values here, though, and it said answer in terms of g, y, and y naught, and m, then I actually couldn't leave my answer like this because I got VB. So what I would have to do is put VB in, which is the square root of 2g times y naught minus y. But all that gets squared over r minus mg. Remember, that's just the velocity at point B. But what's the square root of something squared? Right. M times 2g times y naught minus y over r minus mg. And I guess let's just do it. M 700 times 2 times 9.8. Y naught minus y is just 40, right? Over the radius of the loop was 20 minus 700 times 9.8. This is just the number crunching part, guys, so I'm flying through it because I want to make sure we have enough time for part F. This is the easy part, though. 700 times 2 times 9.8 times 40 divided by 20 minus 700 times 9.8, 20,580. So I get the normal force and put it here. Normal force is 20,580 newtons. Does anyone remember what would happen if VB was the minimum speed to get through the loop? What happens to the normal force at the very top? Goes to 0. So if, when we did this work, we determined that the normal force was 0 at that point, we would actually have determined that, well, that's the minimum speed to get through the loop. But it's not the case. But if it was, then that would be the case. If we ended up with a negative, well, that would imply that we never made it to the top. And it would just roll back. So we didn't have the speed required to get through. The fact that our normal force is much larger than our weight force tells us that we have a lot more than the necessary velocity to get through. And if you've ever been on a roller coaster where you go through a loop and you still feel like you're pressed down, in quotes, down into your seat, even when you're upside down, that's because the normal force on you is far exceeding your weight force. And you feel heavier, even though you're upside down. Right? Because if the normal force is 0 when you're in a loop, then you start coming out of your seat. Right? Or if it gets close to 0, then you feel like you're coming up out of your seat when you're actually coming down out of your seat, but you're upside down. Remember, the normal force is the sensation of the weight. So if your normal force, or if the sensation of your weight is larger than your weight, then you actually feel heavier. You feel like you're being pressed down into whatever's causing the acceleration. Any questions? It's good times, right? It's good stuff. It's good stuff. Now, part F, very often in this class, we deal with situations that are not realistic, i.e. we neglect friction. And that's typical of your introductory physics classes, even AP introductory physics classes, even a lot of physics classes that aren't introductory. You make these assumptions, and then you just kind of deal with the reality a little bit later on. And so part F here says, now suppose the friction is not negligible and that for the coaster to reach point B with the speed calculated in B, which is 28 meters per second, point A must be raised to 100 meters. So my initial height now is 100 meters. Meaning that in reality, if with the friction, we let this guy go from 90 meters and he got to point B, he would not be going 28. He'd be going less than that. Because friction will be doing work, taking some of the energy away. Now, it doesn't just disappear the energy from the universe. That doesn't happen. What it does do is convert that energy to other forms, mainly heat and a little bit of sound energy, but mostly heat. So in order for the actual roller coaster on the actual track to get to this speed at that same height in the loop, that first drop must actually be increased in height by 10 meters, up to a total of 100 meters. And then it says determine the work done by the frictional force as the coaster travels from point A to point B. Now this is why at the beginning I pointed out that saying that the mechanical energy initial equals the final mechanical energy is the same thing as saying that the change in mechanical energy is zero. These are two statements that make the claim that mechanical energy is conserved. If it is not, conserved, then the equation that we write is the work done by the non-conservative force that is taking that energy away is equal to the change in mechanical energy. Right? If the change in mechanical energy is zero, then no non-conservative forces are doing work. If they are doing work, they're taking mechanical energy and converting it to other forms, like sound energy and heat energy. In this case, we're talking about the work done by friction. In reality, this would be the work done by friction and the work done by air resistance, which is usually called a type of friction, which engineers designing roller coasters must take into account. Because you don't want to build a $100 million roller coaster where the top of the first drop is not high enough to get it through the rest of the... You guys know roller coasters work like that, right? When you go over that first drop, no more motors. Nothing's making the car go except for the gravitational potential energy it started with. All right, well, let me write what this means. The work done by friction is the non-conservative force changes the total mechanical energy. It takes some of that mechanical energy away. Well, change in mechanical energy is just final mechanical energy minus the initial mechanical energy. So that's going to be my final mechanical energy. And I like using parentheses here. It keeps things organized in my brain. That's just final gravitational potential energy plus final kinetic energy. That's my final mechanical energy. And then subtract my initial gravitational potential energy plus the initial kinetic. This should make sense. This is my final energy. This is my initial energy. So what this is going to say is that whatever discrepancy there is between these, if I start with 100 joules and I end with 90 joules, that means friction must have done negative 10 joules of work, right, to take that energy away, to take that mechanical energy and convert it to other non-useful forms. Does that make sense? If you lose energy, then this number, right? If you lose energy, then your initial energy number is always larger than your final energy number, so you always get a negative difference. And that negative difference means negative work was done by friction. And remember, if an object moves this way, friction force acts this way. And so the equation work is FD cosine theta. The theta is 180 degrees, so the cosine of the angle is going to be -1. So the work done by friction is always negative. Almost always. There are weird cases where it's not, but for this situation, it's definitely true. But then we just calculate this. And remember that we start with no initial kinetic energy. And then we just plug and chug. So the work done by friction is the final gravitational potential, that's mg times the final height, plus the final kinetic, which is 1/2 m, times final velocity, which is at point B, squared, minus, and if k naught isn't 0, make sure you distribute that negative over both terms. And you got to distribute that negative. But there's only one term in there that's not 0, so that's going to be minus mg times the initial height. Everyone did not bring mass to the party. This guy is a term in this equation, the work done by friction. So doesn't have mass in him. So we actually got to chug all this out. So that's going to be 700, mass 700 times 9.8 times my final height, which was 50 meters, plus 1/2 times the mass times the final velocity, which we calculated already. That's the velocity that we had to raise the initial height to in order to have that velocity at that point in the real scenario where we actually had friction doing work. Minus 700 times 9.8 times our new initial height, which was 100 meters. And then we plug all that in, and we get that the work done by friction is negative 68,600 joules. So that's the difference in the energy there. Make sense? It's a little complicated. It's just adding another term essentially to the conservation of energy equation, though. And saying that the work done is going to be the change of mechanical energy is only conserved if conservative forces act. If non-conservative forces like friction act, the mechanical energy is not conserved. If the mechanical energy is not conserved, then the change in mechanical energy is literally not zero. So this statement here is not true. So that's when we have to say that, well, if the mechanical energy changes, it only changes because of the work that friction does, in this case. And so you just say, well, the work done by friction is going to be that change in energy. And it will always be negative because we always end up with less energy than we had to start with. And if we end up with less than we had to start with, final minus initial is always a negative number. Right? Any questions? Comments? Concerns?